So I'm going to demonstrate the world's most compact, easiest to use M² measurement device on the market. It's the Haas Laser Technologies Beam Waist Analyzer camera. So I have here the BWA-CAM, and we have a 10-watt single-mode fiber laser coming into a focusing head that has a focus lens with an effective focal length of 100 millimeters. And I have a guide beam coming out of the fiber laser for alignment of the camera. This is factory aligned, and I'm just going to simply stick it and roughly get the guide beam centered in the aperture. And I will now turn on the software, hit the play button, switch to the frame grabber screen, and move the camera till I see my spot. And what I want to do is get this spot roughly into position to about right here. Okay, so now this is just the guide beam, and now I can go turn on the fiber laser and see the images of the beam waist. Now we can see the individual time slices throughout the beam waist of this fiber laser in this frame grabber screen. So now if I go to the M² screen, we can see our beam waist caustic. This camera was calibrated at the factory. So in the settings, I have entered the focal length of the lens, the back focal length to the first spot, and then the spacing of the etalons, and of course the wavelength of this fiber laser, 1064 nanometers. And I'm using the second moment measurement for the beam waist size. So that gives us our beam waist caustic. So we have an M² value of about 1.1 to 1.2. And with the camera on its own, our measurement accuracy is about 10%. We've got an astigmatism in this system of about 0.2. I wouldn't swear with this setup that we're coming fully on axis to this lens, so that is probably where the source of astigmatism is coming from. And we have a beam waist diameter of about 28, 29 microns, which fits the theoretical calculation for this spot size and this setup. We've got a beam diameter back at the lens of about 5 millimeters, which is what is the diameter of the beam coming out of the fiber. So everything is corresponding to what is expected. So it's a very simple, very quick, easy way to get the M² and a good idea of how the optical system is working in real time. So we can go back here, and it looks like our focal spot is region of interest number 6. So if I show that here, we can see a fairly Gaussian beam with good false color shape. We can zoom to see all the spots, and they're all very nicely going in and out of focus. And we can create a quick snapshot of the statistics for this system by clicking this button. So now we've got image capture of the sensor, the beam waist caustic, and all the beam waist parameter values, the M², astigmatism, divergence, Rayleigh range, waist diameter, and beam waist position. We can as well log the data of all these values. Now in the single BWA-CAM mode, there are only 5 or 6 options of data that can be collected: the M² value, astigmatism, divergence, Rayleigh range, focal position, and beam waist diameter. These can all be tabulated or saved to a CSV file for later import to an Excel spreadsheet. We can select any of these parameters for quality control purposes and select the upper and lower limit values for any of these parameters to maintain a specific optical setup to be within specifications for some critical material processing application. So the way the beam waist analyzer camera works, if you're familiar with an optical Fabry-Perot interferometer, it looks very similar, except it's used in reverse. So instead of the light coming through the etalon pair first, we actually come through the lens and then into the etalon pair. so that what we see here is an inverted Fabry Pro interferometer. So we have our focusing lens. The light passes through the lens, then hits the etalon pair that are at an angle. So the light is trapped, a small amount of light is trapped in the etalon pair. And with each round trip that's bounced between these etalons, we get a separate focus beam at the sensor. And here we have a close-up, so we've got a spacing, and in this case it's about 300 microns for this setup. So the first beam passes through, heavily attenuated, and the remaining round-trip reflections pass through with a lateral displacement so that we see a displacement on the CMOS sensor, and the time delay is based upon the simple trigonometric relationship so that we have our spatial time slices throughout the beam waste superimposed on the camera sensor. Now, the camera on its own, and the way I'm using it here, it's a wonderful diagnostic tool to see how an optical system is working. Because sometimes the problem isn't the laser, it's an optic in the system. So this camera can very quickly answer whether or not there is a problem with the laser or the optics. I mean, here's an example of a 532 nanometer green fiber laser that is exhibiting a coma in the optical system. In this case, the optics were not focusing as tightly as they were supposed to. It was twice as large as it should have been. And here we see this very nice example of coma, which is not something you want in an optical system because you won't focus as well as you should. In another example, we had a 1064 nanometer fiber laser showing severe astigmatism, where again the optical focusing was off by a factor of 2 due to the astigmatism that's seen. So here we have it showing more focused in the x-axis and better focused here in the y-axis, and then averaging in the center, so that was twice as big as it should have been. So it's a wonderful diagnostic tool for showing different aberrations of an optical system. Another example where this was used was in aligning a multi-kilowatt fiber laser where the delivery fiber was not matched to the source fiber back at the laser, so that we are seeing cladding modes. And this is a very dangerous thing for the delivery fiber, because if the power would have been ramped up, it would have blown that fiber because it's not coupled to the right part of the fiber, and it would have blown the cladding. So by simply adjusting the source fiber to the delivery fiber with the BWA analyzer camera in place, we went from the undesirable condition to what it should have been, about 150 micron spot. So the BWA analyzer camera is a wonderful diagnostic tool, as well as the simplest, most compact method for measuring the m squared of a laser or laser system.